Right, heat equation. Now, what I want you to think about is a one-dimensional rod. I mean, it's a rod. It's a long metallic rod, or it could be some other material. But it's embedded in a wall where it's insulated. So no heat can escape in the other direction, in the radial direction. However, you have ice touching the 2 points. And in Celsius, this is 0 degrees Celsius, right? And then imagine that your rod, this iron bar, initially has some temperature, room temperature like 20 degrees Celsius, right? And then it touches the ice, and then the temperature will drop starting from outside, right? So you can imagine the graph of the temperature, which we're going to say uxt, will be the temperature at time t and location x. Okay, so the graph should look like this. You have initially when time t is equal to 0, let's say it's at 20 degrees Celsius. So like from end to end it's 20 degrees flat. But then once you touch the ice and you let the heat dissipate, like a moment later it's gonna the endpoints will be dropping down to 0, right? So what you're gonna see is right after, do I have other colors? Yeah, I have green. So, oh, that's black either. Okay, well, I'll just use this. All right, so it's going to drop, but you know, the thing in the middle will drop less fast than the ends, right? So because this will keep heat more than the opposites, right? And then you're going to have that, and then later you're going to have t equals to 2, t equals to 3, and then the heat will continues to drop. The temperature will get closer and closer to 0, but then the closer the temperature is to 0, the heat will dissipate slowly. So only at time infinity it will be completely 0 everywhere. That's what we're going to expect. Okay. Now, the goal of today's lecture is to actually come up with a differential equation explaining this and solve it, and also draw the graph to show that it does look like this. Now, we wouldn't have time to actually draw the graph on the computer, but next time I'll surely show you the graph, and it will look like this. Okay? All right, so let's try to think about the derivation of the heat equation. And for the derivation of the heat equation, one way to do it is to use the Newton's law of cooling. You remember that formula where the rate of the change of the temperature is proportional to how distinct the object's heat is to the surrounding ambient temperature, right? You can use that, and then you can derive it, but that's really complicated. And what I'm going to do is actually, in some sense, it's actually more intuitive than deriving it that way. So let me just talk about derivation briefly. So think about the following. If you have a heat distribution that's like this, so you have higher heat here, lower heat there, okay, then what do you think would happen to this point here? Would the heat go down or go up? So U is the heat, or the temperature. And temperature, if you look at the rate of change of the temperature at a certain location x, right? And you look at the rate of change with respect to time. I should really say U is a function of x and t. Would this be positive or negative? What do you think? Yeah?
Negative.
Yeah, don't you think it's gonna, I mean, of course, there nearby there's higher heat, but this is much lower than the right side, right? So it's gonna go down, right? So what you can say is that if you draw a straight line nearby, okay, and if the graph is above it, then it's going to go down. So this will be negative. On the other hand, if you have something that's like this, so that it's concave up, right? So this is called concave down, right? If it's concave up, then this will be positive, right? It'll be increasing. This point right here. Okay. And not only that, you should be convinced that the bigger the concavity is, the faster it's going to increase, right? So if it's like sharply concave, right, then it's going to increase really fast, right? Or if the concavity is negative, right, and then it's very sharp, then it's going to decrease really fast as well, right? Now, what gives you the concavity? You did this in Calc 1. To get the concavity of a function, you calculate? Huh? Second derivative, yes. So, I don't know who taught you calculus, but in calculus 1 I drew this. Do you know this picture?
No.
Okay. What does this mean? If the second derivative is positive, then it's concave up, right? If the second derivative is negative, then it concave down, right? Yeah. So this is the case where if you differentiate twice in the x direction, this is the case when it's negative. So when this is negative, this is negative. When, by the way, I think it's easier to just write this, right? If you differentiate twice in x. Okay, so if you differentiate twice in x, concave up means it's positive, and this should also be positive. Okay? So after thinking about this, you can deduce that the rate of change of the temperature with respect to time, right, should be proportional to how concave it is. Good? Now, we've done this many times in the beginning of the class, at the end of the semester. If you want to have a differential equation model of a situation, then in many cases you know that one is proportional to the other. How do you change that into an equation? What do you do? Ut equals what?
Constant times.
Yeah, so you write down k, the proportionality constant, right? Yeah. So we put constant of proportionality, and you write like this. And basically what this k does is that if the k value is big, then the material has very fast heat dissipation. If k is small, then the heat dissipates slowly. And of course, it depends on the material. So If you have something like wood, then K would be somewhat small. Metal, on the other hand, it will have rather high value of K, and even between metals it might have different values. I have no idea what these values would be. But I know that in general this should be the differential equation for the heat. Okay, convinced? So if you're convinced, now let's title that equation as the heat equation. So now we're going to say UT equals to K times UXX as the heat equation. But then in addition to this, there's some other conditions that I described here that you have to figure out how to write. So let me talk about the boundary condition, because at the two boundaries is touching ice, right? So one way to talk about this is to say that the value of the temperature, and by the way, x equal to 0, 0 would be the left side, and let's agree that L is the length of the bar. So when x is L, that will be the right side, okay? So that's how we're going to do this. So if you evaluate the temperature at 0, x equal to 0, or if you evaluate the temperature at L, they're both going to equal to 0 because they're touching ice, okay? And this one is what we call the boundary conditions. Now, there are several other boundary conditions you can think of. Maybe you want to put some hot boiling water here so that one side is 0, whereas this side would be 100. Boiling water in Celsius is 100. That's possible. And I will later try one question that will be looking like that. But the zeros are the easiest, so I'm just going to do the zeros first, okay? Once you learn how to do this one, then you can modify the solution to solve the one for where the right side is, one side is 0 and the other is 100. That's also possible. Okay. And then also, there should be some initial temperature distribution, right? I mean, I want to solve the case when the bar is evenly room temperature as 20, but you could very well think of a case where the initial temperature distribution is like this. You have high temperature at the middle, could be shaped like that, right? So we will just write in general that U x t, no, x0, sorry, x0 equals to f of x. Say, I said time t equals to 0, so that means that's the initial heat distribution, and that's equal to f of x, some given function, okay? Could be a constant function 20, which we'll be using later, or it could be a function that's like that, or it could be any kind of function that you use, okay? So it's some function, and this has the name of initial condition. Obviously, because time t equals to 0. Okay, so that will be the general form of the differential equation we will be solving. And there's some other kinds of modifications of this where instead of the values at 0 and L, you might have you differentiate by x equals to 0. We'll do some modifications later on. Okay. Now, what's important here is that if you provide the boundary condition and the initial condition to a heat equation, then some smart guy proved that there always will be a solution, and if there is a solution, it will be unique. There's only one unique solution to such a system. Okay? which, by the way, physically it makes sense, right? If you have some initial condition of the heat distribution, and you initially like this and touch ice, and then you look at the way that the heat is progressing, you would very well physically can imagine that such should have a solution, right? So just our physical intuition should say that, of course, this should have a solution, but it's also possible to show mathematically that this has a unique solution by using something called energy. Yeah, but we're not interested in that. We just want to use that to do what? Why is that important to us? That the solution exists, and if it exists, it's unique. Why do we like that? Because are we solving differential equations? Do we solve differential equations? No, we don't. What do? We make guesses. We make educated guesses, right? And even if we were just making guesses and getting it somewhat right, as soon as we make it right, we find something that satisfies it, then because of uniqueness, we have found the solution. That's the argument that we want to make. So such a uniqueness theorem or existence theorems are very important to us, even though we never bother to learn how it works, nor we can prove it. It's just given to us, and if that's given, we just gladly use it. By the way, unfortunately, it's not true for all differential equations. Notably for Navier-Stokes equation, we don't know uniqueness or existence. But because the system comes from some physical arguments, and in reality fluids behave like the Navier-Stokes equation, we just still solve it almost by guessing, rather than even if we don't have guarantee that the solution exists or it's unique. Sometimes we don't have a choice. But at least for this, we know that the solution exists and it's unique. Okay. All right. So that's all the background knowledge then, and I can now start showing you a question. Okay. So our very first PDE question. This is called a partial differential equation because the derivatives are partial derivatives, right? And it's a PDE of second order because you have two derivatives in x. Okay, so we're doing a second order partial differential equation, which is very hard, and it's your first time seeing a solution of a PDE. Yeah, so prepare to be amused. See how you can do this. Okay. All right. So we're going to change this a little bit. We're just going to take k as 0.2. I just thought about that number randomly. L I'll just take as 10. And then, as I promised, we'll do the room temperature. 20 degrees Celsius is room temperature. So that initially it's like this, and then you want to verify that solution is like this. Okay. And we want to solve this. Solution. Okay, the first step, step 1, and we're still working with the spirit of guessing. We are not trying to solve everything at once, and what we do is we just look at this much. We just look at this much right here. So, and we try to solve as much as possible. And by the way, to give you an idea of what we're doing, it's like, think about the second order differential equation. We have like y double prime minus 5y prime plus 4y equals to 0. How did we solve this? We start out by putting some ansatz, right? We assume that, the solution should look like that, right? We plug that in, And you end up with the condition for r, in which case it'll be r squared minus 5r plus 4 equal to 0, right? And you get that r must be 4 or 1. That gives you two solutions, e to the 4x and e to the x, right? What do you do with them? With these simple solutions, we take the linear combination of them, right? So that's your general solution. And if there's an initial condition, y of 0 is 1 and y prime of 0 is 2, then what do? You just plug that in to figure out C1 and C2, right? So that's what we're doing. We're right now trying to find the general solution without the initial condition. Make sense, right? And at this moment, we're just going to assume that the solution takes some special form, and that will give us some building blocks for the general solution. That's what we're going to do. Okay? So what we're going to do is look for all solutions of heat equation plus the boundary conditions in the form of uxt equals to x of x times t of t. Okay, so this is going to be our Ansatz. Ansatz. German word for sentence. It's like thing that you use when you're trying to guess. Right? I believe the solution should look like this, and you take some form and you plug it into the differential equation and see what it gives you. Okay, and then from that, sometimes you get enough hints to construct what these should be, and you're done. Okay, so that's going to be our Ansatz. Should I erase this? I'll leave that, so please don't. That's totally unrelated, so ignore this, okay? Now, let's see what this ansatz is saying. This ansatz is saying that the function that we're looking for should be a form where you have a pure function of x, a function just purely of x, and another function purely of t. So, I mean, not all functions can be written this way, like xy plus, no, xt plus 5. You can't really make this as a product of a function of x and function of t, right? So most functions you can't do that, but you're assuming that this is what we want. Okay? And because you're separating the x and the t, this format has a name. The name is separation of variables. Okay, so it's called method of separation of variables. I don't have to spell it, right? Separation of variables. Variables meaning x and t, the two variables are separated. Okay. SOV is a pretty common acronym for separation of variables, so often you'll see this used in some papers as well. Now, I also want to add that in fact this kind of solution is physically motivated, because if you have this solution, initially it doesn't look like that. The shape does, like initially when time is like a split second later, it more looks like a square rather than a parabola. But at some point, as it goes down, more and more, it looks as if the shape of the graph is almost the same. The only thing that's changing is this amplitude. So you can kind of have some intuition that some solution of this heat equation must be like the shape of the graph stays still, but there's some function which will make it smaller and smaller. So this t of t, what it does is, as time becomes bigger, this value just becomes smaller and smaller, so that for a fixed value of t, when you draw the graph are just rescaling of the previous graphs. Okay, and that's where this intuition comes from. So, physics helps a lot when math becomes harder. Knowing the physics, someone thought about this. Okay, so maybe some solutions might look like this, and then you plug it in, and you can get some results from it. Okay. All right. So let's plug this into the heat equation and see what we get. Okay. First, remember this is a partial derivative, right? Partial derivative means you treat the other variable as a constant. So if you differentiate this by t, this is treated as a constant, right? So what would you get if you plug this on the left side?
You get x of x.
X of x times. See, that's a constant, so that stays as it is. And then? Yeah, derivative of t. T prime t. Okay, on the right side, you get 0.2. What would you get for uxx?
Get t of t.
Yeah, t of t doesn't change.
X of x double prime.
X double prime, yes. So that's what you're going to get. Hopefully, naming this function as x and naming this function as t is not going to make you confused. I could have done fx times g of t, but naming it this way makes it easier to remember which one is which. If I name it as fx and gt, then I have to keep telling myself that f is a function of x and g is the function of t, so I don't like it. So, is that okay?
Yes.
Okay, so that's what we have. Now, let's work on this later, okay? So let's just use this. Now, one thing that you have to memorize is that every time you plug in the separation of variables ansatz into the heat equation, the first thing that you have to do is you have to divide both sides by k times tx. Always divide by ktx, where k here is 0.2. T is a function of t, and so on, okay? Or kxt. I like ktx. It's like a name of a railroad in Korea. Why am I saying that? All right. So you have x times t prime of t divided by 0.2 xx tt equals to 0.2 x double prime of x t of t over 0.2 xx tt. And then we cancel the x here, 0.2 here, tt there, and we have a nice equation that says t prime of t over 0.2t equals to x double prime of x over x of x. And once you have this, it looks a bit strange, because on one side you just have t, on the other side you just have x. Now if it doesn't look that strange to you, let me explain this a little bit more, and you'll see why I feel that this is strange. First of all, in a differential equation, all equal signs are equality of functions, right? The two sides are equal as functions of x and t. So if this is true, then both sides should be equal for any value of t and any value of x. Okay? Is that good? So this is a function of t, and that's a function of x, and they should be equal to each other for any value of t and any value of x. But usually that doesn't happen, like, think about this. If you have like a function of t, say t squared, and a function of x as x squared, is this true?
Only for certain values.
Only when t and x are equal or negative of each other. Usually they're not true. If t is 1 and x is 2, it's not true that they're equal, right? So it seems like an impossible condition to satisfy. However, if you think a little bit harder, you do see that there's one case where both sides can be equal. Okay? And I also want to add that if you took this question and gave it to a really smart person who has learned everything that we learned so far, and that person's first time seeing this, there will be like 2 steps that that person will be stuck. And the first step is like thinking about this, right? That they'll, like, I think people have to spend a long time that this is the way to go, okay? And then if that person indeed was given this hint and did the work, he or she might be able to go up till here, but then that person might be stuck right here, not knowing what to do after this, okay? So that's like one of the crucial moments of the solution when you do separation of variables. Let me kind of explain like this. This is a function of t. So you can view this entire thing as a function. Since this side says it's a function of t, it must depend on t. And since this side says it's a function of x, it should also depend on x, right? So for this and this to be equal, it has to equal to some function of t and x, right? How can that happen? What kind of function, f tx, should it be so that this equality can happen for all x and t?
Does it have to do with partial derivative?
Right now, there is no partial derivative involved. You know, babies sometimes they're sitting on a small plastic table and they have a bunch of things to play with, right? And you have all these controls that's supposed to do something, like there's like a machine-looking thingy and then 2 dials, and it's supposed to say that if you change this dial, then something should happen there, right? But they don't do anything. The babies still play them. But if the thing in the front panel is not reacting to any changes on this, what kind of panel is that? It doesn't change, right? It's the same situation here. Look. This function, if you look at it right here, for this to be equal to that, changing the x value is not going to change this. Do you agree? Right? So for this to equal to that, that means this function is indifferent to the changes in x. Right? Now look at these 2 identities. For this to equal to that, this function should be indifferent to changes in t. That means, what kind of function is this?
Constant?
It's a constant function. So that's the logic, right? Now, if you don't like that, you can make another argument like the following. We agreed that these 2 should equal to each other for any values of x and t, right? So just think about what happens if you plugged in 1 here. So you get x double prime of 1 over x of 1. Now, then this should equal to this for any value of t, right? I don't know what this value is, but it's some constant, right? So I plug in, I shouldn't be putting small x. It should be capital X. All right. So this is some value, and this has to equal to this for all value of t. But that means this doesn't depend on t, right? If this is always equal to a single value, what kind of function is this? A constant function. Again, that's another argument. Okay? So this separation of variables, the core argument is right here, where you say, oh, once you separate the variables on one side and to the other side, then the only way the two sides that can equal to each other is that if they are equal to a constant. And we are going to have to name that constant, and we will always name that constant as negative lambda. Now that's just a choice. Let me put it as blue because I want to say that that's some agreement that we'll always make. See, I could still make that argument by just dividing by xt. Just dividing by xt will still have t on one side and x on the other side. And I can still name that constant as some c or whatever, k or some other, some beta or alpha or anything. However, it streamlines the process if you choose to always divide both sides by ktx, and also choose to name this constant as negative lambda, and you'll see why later. It just makes the solution cleaner, right? So just keep that in mind. Let's continue on. All right, so this now gives two equations. So the first one, this one equals to this. If you solve by multiplying this to the other side, you get t prime of t equals to negative 0.2 lambda t of t. And the second equation, if you multiply x of x to the other side and move it to the left side, you get x double prime of x plus lambda of x equals to 0. You see, so hopefully I don't have to show you the algebra. I multiply this and move lambda x to this side. Okay? So that's what we get from the heat equation. Okay? Now let's plug in uxt, xxt, t into the second equation. What would you get if you plug this on the left side? Huh? What do you get? X of? You plug this into the left side. What do you get? Come on, what is u of 0t? What's u of 0t?
X of 0.
X of 0, right? T of t, right? Now what is u of 10t? Right? And that has to equal to 0, right? Okay. And then let's think about what x of 0 times t of t equals to 0 means. This means that either x of 0 is 0 or t of t equals to 0. However, I don't like t of t equals to 0. Why would that be bad? What goes wrong if t of t is 0?
Basically just 0.
Huh?
A lot of things go to 0.
A lot of things go to 0, especially which one? Which one's 0? If t of t is 0, which one is 0? The most prominent one, the one we are after.
The lambda.
No? By the way, if t of t is 0, this wouldn't be defined, but that's not the point.
Small t.
No.
U to that.
U. This is the solution. That the solution we're looking for will be 0. Why don't you like u being 0?
Because then you found nothing.
Then you found nothing. What do you call it?
Trivial.
Trivial solution, yeah. Because u equal to 0 is already a solution to this without having to do any work, right? If you have a constant 0 function, of course it's going to satisfy this equation and this equation. But that adds nothing to our knowledge, so that's called a trivial solution. So this is going to lead to trivial solutions, so we don't like it, okay? And therefore, in order to get a non-trivial solution, you better have x of 0 equal to 0, okay? To have non-zero. The same deal to the second condition. X of 10 equal to 0 should force that x of 10 must be 0. Okay? T of t cannot be 0. And now, look at what we have. We have x of 0, first, this equation here, x double prime plus lambda x equals to 0. Right? And then x of 0 equals to 0, and x of 10 equals to 0. And we want to look for non-trivial solutions. Where have you seen this before? We actually solved this exact problem on Thursday, right? Yeah. Agreed? Yeah. All right, let me change the ink. Okay, so if you can go back to your notes, can you tell me what the solution was? Okay, who found the solution? Yeah?
Lambda was n squared pi squared over 100 for n equals 1, 2, 3, and so on. And then y equals sine of n pi over 10x.
And yeah, so we are naming as y, y
X.
double prime, but in our context it'll be x, right?
Yeah.
So x of x should be sine of n pi over 10 x. Okay. Now, we can further, and by the way, let me delete this one. Continue on here. We can further plug in the value of lambda here and try to solve for t. So t prime equals to negative 0.2, or 0.2 is 1/5. So let me write 1/5 times n squared pi squared over 100 times t. And we know very well what kind of function will give you a derivative some number times itself. It's the exponential functions, right? So we know that t must be some constant times e to the negative n squared pi squared over 500 t. Okay? This function, if you differentiate, this number will pop up in front, satisfying the above equation. Okay, is that good? So in general, I'm saying if t prime is equal to kt, some constant alpha t, then t is always c e to the alpha t. That's all I'm saying. Okay. All right. So we got x and we got t. Oh, I erased what our original u was. What was our u? What was our definition? I forgot already.
Equals x t equals x t.
Tt, right? It's a product of these two functions, right? So you multiply these two and you get c e to the negative n squared pi squared over 500 t times sine n pi over 10 x. That's what you get. And that's all the possible solutions of the form where your function of x and function of t are separated. Okay. Now going back to this analogy, so it's like we found one solution, another solution. By the way, how many solutions is this? Infinitely many, because n could be 1, 2, 3, 4, 5, right? Okay. So what's next? Once you find these building blocks, how do you write the general solution? Take the linear combination, right? So what do you get? Summation, and from 1 through infinity. So it could be C1, C2, C3, but instead of having just 2, like here, you have infinitely many. So sum from Cn e to the negative n squared pi squared over 500 times t sine n pi over 10 x. So you found all the building blocks, multiply them, and take linear combinations, but instead you get infinitely many. Okay? So this is like having your general solution, the C1, C2, undefined. Okay? To find the C1 and C2, what do? You plug in the initial condition, right? So with that same analogy, now it's time to attack this initial condition, right? So that's going to be step 2. Okay. Now I only put 2 steps, so it sounds really simple, but it's not. Yeah. But I'll just still write step 2. Step 2 is apply initial condition. Okay, so let's try to apply the initial condition, which is that I take this equation and take t equals to 0. If you plug in t equals to 0, if you plug in 0 here, you get ux0, but ux0 is 20, right? So you get 20. By the way, this 20 is really 20 as a function. It's a heat distribution. It's a function, constant function. You could have questions where it's not 20, but some function of x as well. Right. So it's equal to 20. And then on the right side, if you plug in 0, what do you get? Summation of n equals to 1 through infinity of Cn times e to the 0th power times sine n pi over 10x. But e to the 0th power is just 1, right? Yeah. So it's just 1. So you just have this. What does that look like? Yes? It's the Fourier sine series, right? So you're trying to represent 20 as Fourier sine series. Okay. So just I'll give you the formula for the Fourier sine series. The Fourier sine series goes like this. If you have a function of x, and if you want to represent this as summation n equals to 1 through infinity of bn sine n pi over lx, then you obtain the bn by this formula, 2 over L integration from 0 to L f of x times sine of n pi over Lx dx. Okay, so that's the formula for the sine series, Fourier sine series. Okay, so that means that since our function is 20, 20 is not a number, it's a constant function, so I need this. And then what should our L be? Any idea? 10, because it's n pi over 10, right? N pi over L. Okay, so that's good. So we can now calculate Bn as 2 over 10 integral from 0 to 10 of 20 sine n pi over 10 x dx. Now let me bring the 20 outside. 20 times 2 is 40. 40 divided by 10 is 4, so it's 4. If you just integrate this one, sine integrates to negative cosine. And n pi over 10, the reciprocal comes outside, so it's negative 10 over n pi times cosine of n pi over 10 x. And then you have to plug in 10 and 0. Now, if you plug in 10, you get cosine n pi. What's cosine n pi? Negative 1 to the nth power, because cosine values become positive. Let's see. At cosine pi, it's negative 1. Cosine 2 pi, it's positive 1, and so on and so on. It alternates between negative 1 and 1. So it's going to be negative 40 over n pi. When you plug this in, it'll be negative 1 to the nth power. Minus negative 40 over n pi. And when you plug in 0, what do you get? 1. Right? So it's just 1. Since minus minus is plus, and if I factor the 40 over n pi, I get 1 minus negative 1 to the nth power. Okay? And once you plug that in here and compare these two, Cn is exactly Bn, right? So here's what we get. I said this is Bn, but that's really Cn. Okay. So we found the coefficients. What's the answer? How do you write the answer? If you find the coefficients, what's next? Yeah, you just plug it back here, right? So the final answer. So, all right. So we now can write down the final answer, which is uxt equals the summation of n equals to 1 through infinity of, this should be 40 over n pi, 1 minus negative 1 to the nth power, e to the negative n squared pi squared over 500 t sine n pi over 10 x. So this is the solution, and in the next lecture I will actually use a computer to plot this. Of course I'll have to, I can't do infinite sums in a computer, so I'll have to truncate it. But if you draw it, you will indeed get a graph like this. That'll be fun. That's all.